Section 21. Dark Ages, First Stars, and Reionization. The Dark Ages start sometime after 370,000 years, redshift of 1090, the end of recombination. After recombination and CMB last scattering, the scale factor continued to increase, and density and temperature continued to decrease. There were no stars yet, no star light. After last scattering, the temperature of the CMB was 3000 Kelvin, visible orange light throughout the universe, but fell below 140 Kelvin before the first stars would form. The CMB background light did not abruptly become dark and visible light. First, the light would have gotten redder and dimmer, and then even redder and dimmer, then dark invisible light, but still glowing in infrared light. Around 1 million years after the Big Bang, CMB temperature was 1630 Kelvin, dark orange, and the average ordinary matter density of the universe fell below the matter density of the best vacuum created on Earth. Around 3 million years after the Big Bang, CMB temperature was 800 Kelvin, no longer visible to our eyes. We will take this as the start of the Dark Ages. This image is showing that as blue, but it should be black. Around 10 million years after the Big Bang, the total matter density of the universe fell below the present matter density of the Milky Way galaxy. There had been slight overdensities of dark matter since before CMB last scattering, and some baryon ordinary matter overdensities got frozen in at last scattering. Subsequently, dark matter overdensities increased, gravitationally attracting dark matter from nearby regions. Ordinary matter overdensities increased, gravitationally attracted to dark matter overdensities, and gravitationally attracting ordinary matter from nearby regions. Regions contracted that would later be galactic superclusters containing contracted galaxies containing contracted stars. First stars shine at 50 to 400 million years, redshift Z of 48 to 11. And this is the end of the Dark Ages, the start of the Reionization epoch, shown as stars forming here and the Reionization epoch here. Cosmologists believe that the first stars started to condense, begin fusion, and shine sometime between 50 and 400 million years after the Big Bang, ending the Dark Ages. The redshift for that time is between Z equals 48 and Z equals 11, so we see their starlight redshifted into the infrared. The Hubble Space Telescope cannot see these first stars, but the James Webb Space Telescope should be able to see early galaxies with the first stars to shine, and early quasars. Over the next few years, the James Webb should provide better understanding and confidence about the first stars and first galaxies to shine. The first stars to shine were probably more massive, hotter, and more luminous than the Sun. they emitted a lot of ultraviolet light. This reionized nearby hydrogen gas that had been neutral since recombination and throughout the Dark Ages. There would be a large bubble of ionized hydrogen plasma around each star. As more large, hot stars formed and shone, and also quasars at the core of galaxies, more of the hydrogen reionized, and there would be an ionized bubble around each galaxy, and then extending between galaxies. Larger and larger bubbles. Reionization completes sometime between 650 and 1200 million years after the Big Bang. So Z in the range of 8 to 5, and that is the end of reionization. All the hydrogen in between galaxies is fully ionized again. And it is that way today. Cosmologists believe that all the hydrogen in intergalactic gas and cosmic voids throughout our visible universe became fully ionized by 650 to 1200 million years after the Big Bang. Z in the range 8 to 5. So between 50 million years and 1200 million years is called the reionization epoch. We cannot see the emitted ultraviolet from those early stars that was absorbed reionizing the hydrogen. When reionization finished, the intergalactic medium stopped absorbing the ultraviolet light because it was fully ionized, and that ultraviolet light then traveled the universe. So we can see the ultraviolet from Z equal 5 quasars, but not always from the more distant ones. Lithium would also have become ionized in some portion of the intergalactic helium, but I don't know how much. Cosmologists have this interesting history of our universe in 15 seconds. First there was nothing. Then there was something. Then there was hydrogen. Then there was dirty hydrogen. First the dirty hydrogen was ionized. Then it was neutral. Then it was ionized again. So intergalactic hydrogen was once again a plasma, as it was before recombination. However, the universe had expanded and the density of hydrogen ions, electrons, and photons was more than 1,000,000 times lower than before recombination. Photons could scatter off the plasma, but the rate of scatterings was 1,000,000,000,000 times lower than before recombination. The plasma is not opaque but not fully transparent either. Cosmologists believe that about 1 out of 16 cosmic microwave background photons have scattered off the reionized hydrogen. So there is some fuzziness to the CMB imaging. If you want to read more, you should also read about the Lyman Alpha forest. Astronomers and cosmologists want the James Webb Space Telescope to identify the times when the first stars, galaxies, and quasars started to shine. Astronomers and cosmologists also want to know how early galaxies, stars, and Type 1a supernova were different from today.